Hi, I'm Rachel, representing Rutgers in AISC Student Steel Bridge Competition 2021. Go Scarlet Knights! We wish we could build our bridge in person, but we are grateful for the opportunity to participate in the supplemental competition. I'd like to thank Isaac, our team captain, for leading us online this year, and Dr. Najim, our faculty advisor. Let me introduce the rest of our team. Beginning with the seniors, we have Sarah, who's majoring in civil engineering, and myself, also majoring in civil engineering, looking to go into structural. For the juniors, we have Isaac, who's majoring in civil engineering, Lakshmi, who's majoring in civil engineering and minoring in economics, Kathleen, who's majoring in civil engineering and looking to go into structural, as well as Josh, also majoring in civil, looking to go into structural, and TJ, who's majoring in civil engineering, looking to go into construction management. We have one sophomore on our team, Nikita, who's majoring in mechanical engineering. So in the spirit of COVID, social distancing, and remote work, our company, Scarlet Structures, would like to present our bridge to the owner through virtual conference meeting.
Hello, thanks team for coming out today. Thank you for your time to the owners of the project. Hope everyone's doing well and staying safe in these trying times. We here at Scarlet Structures are here to present the proposal for the Katy Trail State Park Bridge. To give us a little bit of background on the project and also how we directed ourselves towards this, I'm going to pass it on to Rachel.
Okay, so as you know, the Katy Trail State Park in Missouri is a very popular recreational trail which spans 240 miles between Clinton and Mackins. However, due to recent flooding, there's now a need for a new multi-use bridge across the waterway so people can continue using the trail. As a design-build firm, our bid package contains a full spectrum of the project from conception to construction. Though all members of the team were included in all aspects of the project, specialization improved the efficiency of the project. Leading the design team, we have Isaac, TJ, and Sarah. The analysis was spearheaded by Josh, Kathleen, and myself, and the construction team was led by Lakshmi and Nikita.
All right, sounds good. Thank you, Rachel. We're going to pass on to the design team.
Hi, guys. So when we first started the design, the first things we had to consider were the restrictions that came with the work site. So our three main ideas were a deck bridge, a Pratt truss, or a Waring truss. And when we weighed both the advantages and disadvantages of all the designs, we decided to go with the Waring truss, and Sarah will explain the disadvantages and advantages.
Okay, so some of the advantages of design is that it's symmetrical, it's sturdy, and it's aesthetically pleasing. It has less building material than most other bridges. Since it's constructed piece by piece, it's more cost effective rather than like looking at the whole picture. And given that it gives more options on how it can be built. And since it has triangular aspects, it makes it even more stronger. So some disadvantages are there may be more parts than a normal deck bridge. Since it's constructed piece by piece, there's going to be a need of routinely checks and maintenance. And the long aspect of the bridge may have some more deflection. So given the disadvantages, it shouldn't be much of a problem to adjust due to the properties of the bridge itself.
Thank you, Sarah. Now we're going to go on to the analysis section. Josh, you ready?
Sure. Thank you, Isaac. And I just want to preface this by saying that after analyzing the design of the bridge, we have full confidence in the performance of the bridge that will be able to handle any of the required loads. So as a summary of our findings, we performed a lateral load test using a 50-pound load in the horizontal direction, and we found that the bridge deflected only 1/100th of an inch in the direction of that load. For our first loading scenario where we considered vertical deflection, we found that the bridge deflected 0.0306 inches at the D1 location that was specified. It deflected 0.0279 inches at the D2 location, and it swayed a negligible amount. Our second loading scenario that we used, we found that the vertical deflection of the bridge was 0.0309 inches at D1, 0.0296 inches at D2, and similar to the first scenario, it did not sway a significant amount. So to come about these results, we performed both computer analysis and hand calculations involving no less than 2 people, both performing the calculations and checking the calculations. So we use both 3D and 2D modeling, and I'll bring up on my screen one of the 3D models that we used. So here we use SAP 2000, and you can see here a rendering of the bridge with the loading in pounds per inch, and then the approximate deflection that we calculated for the first scenario of loading. So we wanted to make sure that this 3D model had as close to the sectional and material properties as possible to what was designed, and that the geometric considerations would be as close to the actual as designed. To talk about how we verified these calculations and these models, I'll pass it over to Kathleen.
Thanks, Josh. Yeah, so to begin, what we did was we took a single beam, which was representative of the south stringer, and we found the moment and shear diagrams for the stringer. Josh pulled it up on the screen so you could see some of our hand calculations. So after we got the moment and shear diagram, we then moved on to the actual truss analysis. So using method of joints to find the axial forces, and we did this for both the north and south side, and we also did it for all the members, like we said, and this was to aid in our deflection of the certain locations that Josh had previously mentioned. After that, we then used principle of virtual work to find the deflection. So we did the truss analysis again, except just for the virtual trusses for north and south to get our overall deflections. Then after that, we talked about the lateral load test. We had to keep it very simplified for the hand calculations, and we are primarily going to be focusing on our SAP analysis and the results we got from that, since it takes into account the bracing and more of the stiffness of the overall bridge. So this is a very simplified calculation, and our sway definitely is higher than that of SAP, but it's nothing that we are concerned about because we are taking into account less of the stiffening features. And then we went through the buckling. We did it for local and flexural buckling, and both of which were good. So everything passes, like Josh had mentioned, and we have confidence in our performance of the bridge. So Isaac?
Thank you, Kathleen. So that handles most of the conceptual project part. We'll go on to construction. Lakshmi, you ready?
I am. So basically with the construction sequencing, our goal was to have a plan to make it as cost effective and as timely of a build as possible. And given the design of the bridge and the materials that we were given to work with, we decided to have a few components to the plan. And so our main plan would be to have 4 builders on the site in total, 2 on each side. And the materials that will be needed on the site include 4 stub nut drivers, 4 leather pouches to carry materials back and forth, 4 hard hats and 4 safety glasses respectively to enforce safety standards and procedures, and finally 97 nuts and bolts each to help assemble with the connections. The sequencing that we've decided to go off of is what we call a diagonal crossover, which is when there will be 2 builders on each side, and on each side they'll start by building the footing and then assemble the decks on their side respectively, and finally assemble the trusses, and then once both sides are completed, they will come together from a diagonal crossover. It's a rather innovative way of construction just because this type of building has never been done before by prior companies, and we think that this will be the best way to build our bridge effectively, and we hope to inspire other bridges to be built the same way as well. The total construction time is estimated to take about 27 minutes, as that's based on the factors taken into account with construction sequencing, the number of members that need to be connected, and as well as in-site travel during our building time. And the construction cost is estimated to be about $8 million, and the total cost is estimated to be about $9 million. And that's also taking into account the construction, structural, and material costs that are associated with it. And my associate, Nikita, has put together an animation for you to see exactly how our bridge will be built. So Nikita, can you please show them?
Sure, no problem. So first, we're going to start with the supports, which will be located on the 4 sides that are given to us. We'll then be doing the stringers with the cross method as described by Lakshmi. Then we'll focusing on the bracing to support the 2 stringers together, so then we can work on the truss, which will then be assembled in the individual pieces as shown below. Finally, after all of that is complete, we'll finish off with the bracing at the top of the truss.
Thank you, Nikita. That is our construction processing and sequence. Let's take it back to Isaac.
Thank you, Lakshmi. Thank you, Nikita. So with that concludes our proposal for the Acadia Trail State Park Bridge. Thank you, everybody, for coming out today, and we hope to hear back from you here at Scarlet Structures.